Hello and welcome to today's video. In today's video, we continue looking at energetics of reactions. Now, for today's video, we are going to focus on what we call bond energies. Now, before I dive into bond energies, I would like to give a recap on what is important or what we need to know with regards to energetics of chemical reactions. So, when you're given a general reaction of this nature, A reacting with B producing AB, provided we balance the reaction, this is considered to be the reactant side of the reaction, and this is considered to be the product side. So we mentioned that the reactant side experiences what we call bond breaking. Then the product side experiences what we call bond formation. Now, bond breaking is known as endothermic. Bond formation is known as exothermic. Now, we can identify an endothermic by looking at an enthalpy which is always positive. Then we can identify an exothermic by looking at the enthalpy which is negative. Now, talking about bond energies, this tells us that each respective bond in a chemical reaction is associated with a specific standard amount of energy. So each respective bond in a chemical reaction is associated with a specific standard amount of energy. Let me give an example of what this means. So if I have A2 reacting with B2, considering those as diatomics, it produces AB. So reducing these two bond energies, I will be given bond and then the bond energy. So bond energy is measured in kilojoule per mole. So I will be provided with a table that shows the standard amount of energy. So in this case, we'll look at the bond between A and A, the bond between B and B, the bond between A and B. So this can be written as A bonded to B, then this can be written as, so this can be written as A bonded to A, this can be represented as B bonded to B, then this can be represented as A bonded to B, but with a coefficient in front simply means that you have two of these. We are saying each respective bond. So this bond has got a certain amount of energy that is measured in kilojoules per mole, which is going to be different from the amount of energy that is existing between B bonded to B. So hypothetically, we can say maybe this is 100 kilojoules per mole, then maybe this is 50 kilojoules per mole, and maybe this is 30 kilojoules per mole. Now, how is bond energy important? So in terms of importance, or how is the bond energy essential? So it's important because it helps us to determine, so we can determine the nature of the nature of the reaction. So by nature we mean when we calculate the overall enthalpy using the bond energies, we can know whether the reaction is endothermic or the reaction is exothermic. So just by looking at this given equation, diatomic A plus diatomic B producing AB, are we able to tell whether this reaction is endothermic or exothermic just by looking at it? So the answer is no. When you're just looking at it, you cannot determine whether the reaction is endothermic or exothermic. So this is where the calculation of the bond energies becomes crucial. So we can use the information of the bond energies to determine the nature of the reaction. So how do we go about it? So I'm going to use the same example that I have given here. So we're saying A2 reacting with B2 producing 2AB. So ensure that the reaction is balanced. Then the bond energy table is always given. So it's a bond energy is in kilojoules per mole. So we're saying A bonded to A, B bonded to B, then A bonded to B. So we said this is 30, this is 50, this is 100. So how do we determine the nature? So we want to know the nature of the reaction, whether the reaction is endothermic or exothermic. So how do we go about it? So the first thing is you have to calculate the enthalpy of the reactants. And remember, the enthalpy of the reactants is endothermic because that is where the bond breaking is taking place. Therefore, you should have a positive enthalpy. So how do we calculate this? So look at A, the energy that we're getting from AA is 100 kilojoules per mole. Then B, we're getting a 50 kilojoules per mole. So when we add this together, we get a 150 kilojoules per mole. Now, because we are dealing with an endothermic reaction, we always present the finding as positive 150 kilojoules per mole. So you always put a positive, and by positive it means that this is endothermic. Then we have to determine the enthalpy of the product, which is exothermic, and it should give you a negative enthalpy. So how do we go about it? So when we look at the product side, Let me use a different color. So product side, we have 2AB, which simply means that we have AB, AB. So this is 30, that is 30. So when we add, this gives us a 60. So it's kilojoules per mole, kilojoules per mole. So kilojoules per mole. Now remember, this is exothermic, therefore your answer is supposed to be accompanied by a negative. So we represent this as negative 60 kilojoules per mole. So the negative is symbolic to mean that the reaction is exothermic. Remember, endothermic is positive enthalpy, exothermic is negative enthalpy. So from here, we calculate what we call the overall enthalpy. So the overall enthalpy is what determines the nature of the reaction. So here, what happens is it's the positive enthalpy, which is for endothermic, then plus the negative enthalpy, which is the exothermic. So this gives us positive 150 plus negative 60. So this is positive, when we do the math, negative 60. So this will give us what? A positive 90 kilojoules per mole. So what we realize is the positive supersedes the negative. So when we get a positive enthalpy, ultimately what that means is the overall energy for this reaction is a positive, which means that this reaction in terms of nature, it's an endothermic reaction. It's an endothermic reaction. So using the bond energies, that is how we can calculate, or that is how we can determine the nature of the reaction. Let me give you another example. Let's say we have something similar to what we looked at. Let's say C2 plus D2 giving us 2CD. Then in terms of bond, then bond energies, which is kilojoules per mole. Yeah, let's say try to do the opposite. So C bonded to C, D bonded to D, then C bonded to D. So let's say this is 20, let's say this is 10, and probably this is 100. Yes. So when we're looking at this, we have to determine, remember, the enthalpy of the reactants. So we calculate the overall enthalpy of the reactants, which is going to be C bonded to C and D bonded to D. So this gives us a 20 plus a 10. So we have a 30 kilojoules per mole. So this is endothermic, so it means that the enthalpy is supposed to be positive 30 kilojoules per mole. Then we go to the enthalpy of the product. So we have a 2CD. So that means C bonded to D by 2, if you like. So it's going to be 100 by 2, which gives us the 200 kilojoules per mole. So the enthalpy is negative 200 kilojoules per mole. So to determine the overall enthalpy, we just get the enthalpy of the reactant plus the enthalpy of the product. So this becomes positive 30 plus negative 200. So this becomes positive 30 minus 200, which gives us a negative 170 kilojoules per mole. So from here, uh, we can conclude to say the nature of this reaction is exothermic, because what supersedes the both reaction, the reactant and the I mean the exothermic and the endothermic, is the negative, which is the overall reaction is exothermic driven. Thanks for watching.